And how good the Riegl is giving us apparent reflectance. Some other groups have done this with their instrument, and we did it with ours. So we're scanning spectral panels with known reflectances from different distances, and then we're looking at how good the Riegl is giving us the apparent reflectance. And I was pretty surprised to find two things with our instrument. The first one is that it's not very good. He's overestimating definitely apparent reflectance. And the other one is with distance, there is kind of a wave in there. So, and it's systematic over all the spectral panels. So around 5-10 meters, we got a low, and then we got an increase in the apparent reflectance around 15-20. So we came up with a little correction factor for these. We fitted a function through the data that allows to at least, if we're measuring wood and leaf at a given distance, let's say 10 meters, at least they're going to be comparable. They're not going to be so different in apparent reflectance to a similar targets that would be, let's say, at 12 meters or 7 meters. So we're not perfectly correcting for this effect, but somewhat here. So this is for the reflectance-based approach. For the machine learning approach, what we did is we added one site here in New Brunswick to the 4 I just showed, which is red maple, pretty low canopy, disturbed, quite young. And we took two 10 by 10 areas within the 50-meter areas that was scanned. One for training the algorithm and one for validating. And then 5 students did the work of tagging points and deciding, is this a leaf, is this wood? So 1 student per side. And we tagged 500 points for each wood and leaf in training plots, and 100 for validation. So we had a total of 5,000 points that were tagged as wood or leaf for training, and then 1,000 for validation. And then we used the random forests. And the training was done on all sites combined. So the results is here. And this is very preliminary. So some of it is somewhat surprising, and we haven't gone through the data yet to figure out why it's like this, but these are the results we got. What I'm finding is, with the reflectance only, although visually results look fairly good, and here I should mention that the students were picking points, selecting points that were fairly hard to separate. So this is making the results maybe look a little bit worse than they really are, but for the reflectance-based method, it's fairly low precision. So we're in the 50-60% range. And with the machine learning here, it's quite a significant improvement in the precision of the separation. So we're going, at some cases here, close to 90% accuracy. In one case, we're staying low, around 55%, and we're still trying to figure out why that is. But to me, this says that clearly the machine learning approach is worth the effort invested in for doing the separation. And the other thing that we learned is that it doesn't necessarily need to be trained specifically on a forest to be applied to a certain forest. So we can train a method and then apply it to a different forest, and it's still going to work. And here we don't have camera, so RGB colored points, so it's essentially just a light variability. So we could go to a new site, collect the data, and use the same algorithm in training, and still get this range of accuracy, which is pretty good. It's encouraging. A note here on leaf angles. Because we're here, I'm talking about mapping leaf area density. Leaf angles is a pretty important factor to consider, and very often it's one that's neglected. So, because it's hard data to get to. For a lot of sites, more and more actually, some sites have walk-up towers, eddy covariance measurements. And I'm taking this note here to encourage people, if you're looking at leaf area density, and especially mapping it, have a walk up the tower and take photographs vertically, because leaf angle distributions in some forests, not all, does change a lot with height. I'm showing an example here from Morgan Monroe. You go to the top of the canopy and you see the leaves. There, most of them are hanging out like this, higher radiation load, so the leaves tend to be a bit more erectified. In this case, it's not totally erectified, but they tend to be much lower. And as you go, not too far, but just in the middle of the canopy, most of the leaves are flat like this, kind of fine. Some other sites that we've seen, like Harvard Forest, we don't see this at all. It's constant, vertically, same thing, very similar. But some sites, this is very pronounced. So I think this is an issue that needs to be paid attention, because very often when we're mapping leaf area in forest, the layer that we're very interested in is the top layer. So we want to get the leaf distribution right, especially at that layer here. So if it's just applying a 0.5 like many people do, will not do the top layer. So on occlusion, I think it's well known that occlusion is an important issue when we're mapping leaf area density. One thing that is a bit more tricky to do is define what is occluded volume when we're scanning with terrestrial LiDAR. And what I'm suggesting here is a definition for what is an occluded volume. So an occluded volume is going to be a volume where you're detecting material necessarily, because there are a lot of volumes in a plot where you're going to have a very low number of pulses going through, but you're not detecting any material. And so if you're wanting to correct for occlusion, it's very difficult to correct for these volumes where nothing was detected. You have no way of knowing, was there actually something in there or not? So the definition I'm proposing here is that an occluded volume is something where at least a pulse, one pulse, hits something. So you know there's material in there, but there's too few pulses that went in to derive meaningful statistics. So this is the way I'm defining occluded areas. And in the past we found that if less than 15% of the pulses that go in, or the theoretical number of pulses that are entering these voxels, if you get less than 15% actually reaching the voxels, then this is occluded. So what I did to look at the level of occlusion as a function of the scanning pattern is that I reduced the density of the scanning. The original scanning, like I said, is done every 5 meters on the 60 meter by 60 meter grid, so we got 121 positions. So I reduced the number of scans down to 10 meter grids, 15 meter grids, and then 20 meter grids. So, for example, the 10 meters in blue will give us a total of 36 positions. And what I'm trying to do here is figure out what's the effect of the scanning density on the level of occlusion. And these are the preliminary results I'm getting for the 4 sites I showed at the beginning. And the one thing I'm learning from that is, of course, the proportion of occluded voxels in percentage levels, it goes down with the scanning density. So here we're at 20 meters between scanning points, and here we're at 5 meters. So on the black here is the proportion of occluded voxels, but it's going down with the scanning density. But that's not the only thing that's happening. In green here is the number of voxels where I detected material. And this keeps going up with the scanning density. So it means that if we're scanning at a little bit of a lower scanning density, we might get some acceptable levels of occlusion following the definition I use. But there's a lot of voxels where there is actually material and we're just not detecting it. So we're unable to correct for it. There's no way of correcting for spaces you've not explored and you have not found any material, have not detected any material. So this to me says that depending on the application you're looking to use the mapping of the leaf area, 10 meters between scan positions could potentially be acceptable, but you are going to have some holes in the data for sure, compared to the reality. At 5 meters, occlusions are getting pretty low, so we're getting around 5% of occlusion. So this is the main findings that I want to present here. Machine learning is definitely worth the effort for separating leaf and wood in terrestrial LiDAR data, which is a major contribution of this terrestrial LiDAR data to mapping material in forest. Leaf angle distribution, if it's possible to observe it vertically, I encourage people to do it. Take a digital camera and then take some pictures at different levels, and then look at the leaves you see sideways in the pictures, and then get the angles from these leaves, and you can derive it's possible to derive functions for the G function. And then a high scanning density is required for most forest types to avoid holes in the data when we're mapping like this. But of course it depends on the application requirements. If 10% holes in the data is acceptable, then I would say 10 meter between scanning positions will get you more in the 15% roughly of occluded areas. So 15% holes in the roof. Getting down to 5 meters distance between scans for us doing this kind of work, it's something like 2 days, 3 days of field work. So it's not bad. So that's it for the presentation.